For decades, science fiction promised us machines that could walk, talk, and work right alongside us. But the reality delivered by engineers looked completely different. Look at these traditional industrial robots. They possess massive physical strength and precision, but they are entirely confined to performing repetitive, tightly pre-programmed motions inside highly controlled factory spaces. Take them out of that perfect environment, and the system breaks down. They simply lack the ability to adapt to chaos or navigate the unpredictable variables of the human world. For decades, engineers had the metal, they had the gears and the motors. The path toward adaptable, autonomous labor was stalled entirely by the absence of a functional brain. At the exact same time, the global economy is facing a massive structural problem. Industries from manufacturing and logistics to global healthcare systems are dealing with severe, chronic labor shortages. To fill those gaps without spending trillions to redesign our entire infrastructure, we need machines that can seamlessly navigate spaces already built for humans. The necessary bridge arrived as digital AI models reached a tipping point in real-time reasoning, language comprehension, and object recognition. This recent explosion in capability is a software breakthrough. By porting neural networks into a chassis, engineers are giving digital intelligence a physical body. By solving the digital intelligence problem first, researchers enabled machines to interact with the world dynamically, turning a distant concept into an urgent economic reality. Tech companies like Tesla, Figure AI, and Nvidia are pouring billions into crossing this software-to-hardware bridge. Instead of engineering a separate machine to do every individual job, they are building general-purpose systems, a single, adaptable entity designed to learn and perform thousands of different physical tasks. These machines rely on highly specialized processing chips to ingest vast amounts of sensory data, allowing the robot to map and understand its immediate surroundings. This diagram illustrates the process. Raw visual input from an unorganized space enters a central processing node, allowing the system to understand spoken instructions, analyze movement, and react to changing variables on the fly. Rather than relying on a human to write new code, the system improves its own physical efficiency through continuous AI training. These modern robots bypass static scripts altogether. They operate as adaptive learning entities, mirroring the trial and error of biological evolution. Tesla's Optimus project highlights exactly how fast AI can accelerate physical hardware development. When Elon Musk first announced the concept, it faced intense public skepticism. Yet today, this prototype can already walk autonomously, carry heavy objects, and sort items in a factory. We do have other highly capable robotic forms, like quadruped designs, serving specialized industrial purposes. But to conquer a world built exclusively with stairs, handles, and tools designed for people, the humanoid form is an absolute necessity. The blistering speed of this development proves the physical chassis is already viable. From here, the upper limit of their capability is constrained entirely by the exponential curve of software updates. The first wave of deployment targets highly structured, predictable environments. Manufacturing plants and distribution centers offer perfect, repetitive tasks to train these early systems. The economic math driving this adoption is ruthless. These intelligent machines can operate continuously on the factory floor, executing physically demanding tasks without requiring breaks, sleep, or a salary. Once the technology matures in the warehouse, the deployment roadmap extends into complex logistics and vital support roles, especially within global healthcare systems straining to support aging populations. But replacing human labor at scale introduces profound societal friction. We are facing the looming threat of massive physical job displacement across multiple global industries. This creates a difficult central conflict. These machines are an immediate solution to critical labor shortages, yet they simultaneously threaten to concentrate corporate wealth and destabilize the working class. Because these machines can learn any human task, they aren't limited to one industry. They are a platform for the entire global labor market, from mining and construction to stocking grocery shelves and cleaning homes. Consider the scale. While a smartphone is a personal device, a humanoid robot is a universal tool for production. If a robot can be deployed for every physical job, the market for this hardware would likely eclipse the size of the smartphone and automotive industries combined. Generative text and image models changed how we interact with digital information. The integration of that exact same intelligence into humanoids will fundamentally change how work is actually executed in the physical world. We no longer have to wait for decades to see if this technology pans out. The advanced hardware and the neural networks are actively converging today. The next major computing platform will not simply fit in your pocket, it will literally walk right beside you. The only remaining variable is how fast society can adapt.